Okay, so yesterday we finished talking about phase transformations, and I just want to re-emphasize a few things. So we have phases of iron alloy, like steel, right? Under the phases are alpha or ferrite, gamma or austenite, Fe3C or cementite. These are the phases of an iron alloy with carbon. These all tell us something about the composition and crystal structure. We know that ferrite is body center cubic, austenite is face center cubic, and Fe3 or cementite is another kind of crystal structure. So those are the phases of a steel carbon, iron carbon alloy. When we talk about microstructure, this is what the material will actually look like under the microscope. And so we have pearlite, bainite, ferroidite. These all have different combinations of the phases. They may have alpha and gamma, or alpha and cementite, or gamma and cementite. So I want to talk about another microstructure, which is Martensite. So Martensite is quenching austenite very quickly to near room temperature. So if we are to look at the phase diagram of iron and carbon, you see austenite occurs in this region. And if we quench austenite or cool it very, very quickly to room temperature, which is below this diagram, right? Because this diagram ends at 400 degrees Celsius. So we're to cool it very, very quickly all the way to room temperature. You cool it so quickly, the material doesn't have a chance to create a nucleus and to grow. Okay, so there's not enough energy for enough diffusion to occur for nucleation and growth. So what does the material do at that time if it doesn't have a chance to move around, if the atoms don't have enough time to move around? It goes through a diffusionless transformation. So it goes from austenite, which is FCC, and it goes to Martensite, which has a body-centered tetragonal crystal structure. So you can think of it, we had talked about diffusionless transformations one time before in this class. I don't know if you remember an example of a diffusionless transformation. We talked about it very, very briefly. This was when we talked about the ceramic material that can be deformed. And so this was one of the supplemental readings. We talked about a ceramic material that can, at room temperature, undergo a compression of 20%, a strain of 20% without breaking. Okay? And the way that that ceramic material was able to do it, remember, deformation generally is the movement of dislocations. But in ceramic materials, because the electrons are localized, it's very, very difficult for dislocations to move. So there is usually no dislocation movement. That's why ceramic materials are brittle. Okay. But in this particular ceramic material that they made, I think it was silicon, don't remember now if it's silicon nitride or silicon carbide. But anyway, they made this ceramic material that it has two very similar crystal structures. And when under compression, the crystal structures can shift slightly. So none of the atoms have to go anywhere, but because of that slight shift, it could change its shape, and so it could be deformed. So that concept is very similar to how Martensite is formed. So Martensite goes from FCC, which austenite, and that's the stable phase at high temperatures, above 727 degrees Celsius, depending on the composition, the amount of carbon, right? It could be higher or lower, but it's somewhere around there. Above that temperature, you have austenite. You lower the temperature, austenite is no longer stable, okay, below 727 degrees C. Normally, what would happen, because it's not stable, it would go through phase transformation. So ferrite would grow. Nuclei of ferrite would form, and then those nuclei will grow until the entire material is ferrite. You bring the temperature down so fast to room temperature, you don't give it time or the energy to form the nucleus or to grow the ferrite phase. But austenite is still unstable. So it's still existing at a very high energy state because it's unstable. So it wants to do something else, but it doesn't have the energy for diffusion to occur. So atoms can't move, or can't move much. So what happens is that the entire material shifts just slightly to a slightly more energetically favorable crystal structure, which is a body-centered tetragonal. So everything moves just a little bit so that it forms a new crystal structure. So it's almost instantaneous. So the formation of Martensite doesn't take much time because there's no diffusion happening, right? So it's almost instantaneous. Everything shifts a little bit and becomes Martensite. Okay, so it is what is called a metastable phase. It's more stable than austenite, but it is definitely not the most stable at room temperature. The most stable phase would be ferrite, but it doesn't have enough energy to form ferrite, so it does the next best thing. It's like when we drew that picture of a block balanced, right? Austenite at low temperatures would be this. It's not stable at all. It wants to do something else. Martensite would be like this, and ferrite would be like that. So Martensite is another microstructure that can happen with the material, and it is formed by quickly cooling. And it is not the most stable, so you're not going to find it on a phase diagram. So Martensite, very interestingly, can make for something called shape memory alloys. So examples of shape memory alloys are copper, aluminum, nickel, and also nickel titanium alloys. These materials also have the austenite phase at high temperatures, and then when you lower them, quench them quickly, they form Martensite, just like steel. So shape memory alloys are interesting because you could deform the alloy at low temperatures, at room temperature. So maybe you have a wire and you can bend it into a new shape. And after you're done using it at that old shape, you want it to go back to its original shape, you just heat it up and it'll spring back to its original shape, and then you could use it again. Okay? And the reason why it remembers what is happening is because it is in the Martensite stage. So you have a Martensite, and you have a crystal structure that is body-centered tetragonal. Because it's formed so quickly, it has a lot of strain. There's a lot of defects in the structure. It's definitely not the same structure all the way through, right? So it's body-centered tetragonal, but it's very disordered. And so when you bend Martensite, you can actually cause some of those distortions or the disorder to realign. So things that are disordered, they could move because the disorder is being reorganized. So it's still not a diffusion-based deformation. So Martensite will deform in a diffusionless way. And so the atoms that are near each other are still near each other. They haven't changed. It hasn't moved. None of the atoms have diffused or moved to a different spot. Okay, so all of the atoms are still near its nearest neighbor, just in a different orientation. And so when you heat it up, the material goes back to austenite, and all of the nearest neighbors are still the same original nearest neighbors. So it remembers its original shape because you haven't moved any of the atoms to a different position. You've reoriented them, but you haven't moved them. And so when you go back to the high temperature where austenite is formed, the material will go back to its original shape. So shape memory alloys remember their shape because there is no diffusion during deformation. Right, so shape memory alloys are used in eyeglass frames, in aerospace applications, in medical applications, and also in automobiles, paneling and things like that. So it's a special kind of, Martensite behaves very differently than all of the other phases and microstructures of metal materials. So it's a special case. But it is used in many applications, so it is important to know about that exception. So in general, metals would deform through diffusion, which is dislocation movement. But in the special case of Martensite, you get diffusionless deformation. So let's talk a little bit more about the different kind of materials and material selection in general. So we've learned about, right now, so far we've learned mostly about metals. And we will learn about ceramics and polymers and things like that next week. But right now, we've learned a lot about metals, so how do we use this knowledge? How do material scientists use this knowledge in industry? So the first material let's talk about is steel, because that's the most common. Steel is iron plus a certain amount of carbon, plus usually some other elements as well. Okay, you've done your material selection project. You're working on that material selection project. So some of you have either steel as your current material or your new material. And so you know that there are different elements that are mixed in. And let's talk about the several kinds of steel. So the first one is low carbon steel. This in general has less than 0.25 weight percent carbon. Okay, so like around here, right? If we look at the phase diagram, this is about 0.25 weight percent carbon. That is a low carbon. That's considered low carbon steel. So what do you think the microstructure will be for low carbon steel based on the phase diagram? If you were to have low carbon steel, what would be the phases present, first of all? We're using this at near room temperature usually, right? So assume low temperatures, alpha and Fe3C. Okay, so ferrite and cementite. And so what would be the microstructure? So these are the phases. Most likely, what would the microstructure look like? Perlite in a matrix of, so it looks something like this, right? So it'd be perlite, but then in between would be alpha or ferrite. Because as we lower the temperature from austenite, you get ferrite forming first, and those ferrite particles or phases stay, and then the rest that didn't convert into ferrite will convert into perlite, which is ferrite and cementite in layers. So you get perlite and ferrite. So perlite and ferrite. So that's what you expect to have in a low carbon steel. It usually is fairly ductile compared to high carbon steel. And we'll talk a little bit about why in a minute. It has high toughness. The high toughness comes from the high ductility, right? It could bend, therefore it could absorb a lot of energy before it breaks. And the way most people work a low carbon steel to make it stronger is through cold working. So by deforming it, introducing more dislocations, making smaller grains, you will be able to make the material harder or stronger. And before we go any further, you will often see steel with a designation of 4 different numbers. So you might see something like 1010 steel. So what those 4 numbers are telling you is that the 1 here is telling you that this is a iron plus carbon material. This is telling you if the percentage of other compounds. And then these 2 numbers are telling you the weight percent of carbon. So 1010 steel has 0.1 weight percent carbon. If you see a different number than 1, usually means that it has other components like manganese or chromium. And then, so let's say a chromium, Fe plus C plus chromium steel would have a number 5 starting here. And then the second number would tell you the percentage of chromium. And the last 2 numbers will still tell you the percentage of carbon. So if we have something like 5225 or something like that, this would tell you this is a iron plus chromium plus carbon steel. It has 2 weight percent chromium and 0.25 weight percent carbon. So if we're talking about a medium carbon steel, We're talking about weight percent between 0.25 to 0.6. Okay, so go ahead and find that on the phase diagram, somewhere between 0.25 and 0.6. So it'll be like around here, right? So we're still talking about less than 1%. So we're still talking about coming down from the austenite phase, still getting perlite and ferrite as we go down. Okay, so the phase present would still be ferrite and cementite. The microstructure is still the same, would be perlite plus ferrite. Medium carbon steels can form martensite. So for really low carbon steels, usually there's not enough carbon to stabilize the structure in the martensite phase, so usually they don't form martensite. But a medium carbon steel will form martensite if you quench it. It is stronger than low carbon steel. Can you think of a reason why it might be stronger? It has the same phases present and has the same microstructure. Why would it be stronger than low carbon steel? It would have more carbon, right? So it has more defects in that sense. Yes. But it would also have more of something else. In its final phase, it would have more cementite, right? It has more carbon, so it's going to form more cementite. And more cementite means that there will be more layers. So a medium carbon steel will have more grain boundaries than a low carbon steel. And so it'll just be stronger and more brittle, harder than a low carbon steel. Okay. And then if we talk about high carbon steels, between 0.60 to 1.4 weight percent carbon. The Wootz steel that we saw that video of, it's a high carbon steel. It has about 1.3 weight percent carbon. So a high carbon steel forms what kind of material? Let's say it's greater than 0.76. Okay, so what are the phases present? A high carbon steel, if we're talking about greater than 0.76 weight percent carbon, we have what phase, what are the phases at low temperatures? What does it look like on the phase diagram? What do you think? Yep, still ferrite and cementite. Pretty much anything, right? At low temperatures, pretty much anything you make less than 6.7 weight percent carbon will have ferrite and cementite. So even high carbon steel, same thing, ferrite and cementite. The microstructure will be a little different than the low and medium. So you will have perlite and cementite. You're forming not just layers of cementite, but actual matrix of cementite and larger particles of cementite when you have a high carbon steel. Cementite, Fe3C, is actually considered a ceramic material because Fe3C, the bonding is not metallic. The bonding between iron and carbon is not metallic. It's mostly covalent. It's covalent and ionic, but mostly covalent. So it's a ceramic material, and so it's going to be very hard and brittle. And so when you have a lot of cementite, your steel will be much harder and more brittle, less ductile. So have lower ductility and lower hardness because of the high amount of cementite. So low carbon steel, a lot of times you will see it used in structures, civil structures like bridges and buildings because it has high toughness, right? It doesn't break easily. And it's pretty strong. Even though it has lower strength than the other kinds of steel, it's still really strong compared to most materials, okay? So low carbon steel is very commonly used in buildings. Medium carbon steels are used in tools, in machines where you need stronger, higher hardness and where ductility doesn't matter as much. And high carbon steel most often is used in cutting tools, like knives, but also drill bits, things like where you need it to be very hard, it can't deform. Okay, drills and knives and things that need to cut other materials. Stainless steel. It's another really common steel that's used. So stainless steel has the addition of chromium in addition to carbon into the iron. And the chromium, what happens is that the chromium, stainless steel just means that it's resistant to rusting. And rusting is just corrosion, right? So when steel corrodes, it forms iron oxide. That's what corrosion in steel looks like. The oxygen from the air, water, whatever, combines with the iron and forms iron oxide. Iron oxide is brown, rust. It's brown and it's very brittle and it's very weak, so it flakes off. And if you get enough rust, iron oxidation going into the material, eventually the material will just break apart, right? So corrosion or rusting is really, really bad for if you need the material to stay strong. And so the reason why it's called stainless steel when you add chromium is because it prevents the rusting from happening as quickly. Rust is brown, and so the metal doesn't turn brown. The steel doesn't turn brown, so that's why they call it stainless steel. Okay, the color stays the same for longer. And just adding chromium doesn't mean that it will never rust or never corrode. It still will, but it slows it down a lot. And the way it slows it down is because the chromium forms oxygen compound, and it forms a layer over the steel, so it acts as a protectant. It's like having a protecting layer over the iron. And so instead of the oxygen reacting with the iron, it reacts with the chromium, forms a layer over the top of the material and prevents further corrosion from happening. And so these are usually used in high temperature applications because the higher the temperature, the faster the oxidation process happens. Or if you have steel that needs to be in corrosive environments, right, near salt water or other kinds of corrosion type of things. Most of the things that you see are probably stainless steel instead of just regular steel. And that's by adding chromium. And then you have cast iron. People don't use cast iron a lot anymore. It used to be used in like cookware. And this is carbon greater than 2.14 weight percent. Okay, so if you look at the phase diagram, you'll see that everything greater than 2.14 weight percent is considered cast iron. The reason why it's called cast iron, if you look at the diagram, greater than 2.14, what's something special about the 4.3 weight percent carbon? If you look at the phase diagram at 4.3 weight percent carbon, what's special about that particular concentration? Right, eutectic. That's a eutectic point where without varying the concentration, if you just lower the temperature, it goes from liquid to two different solids, right? Without going through a liquid plus solid region. Okay, so that's a eutectic point. Eutectic points affect the microstructure. If you're under the eutectic or over the eutectic, it will change the microstructure. But it also shows the lowest melting point of the material, right? If you look at where the material will melt, will become completely liquid, the eutectic is the lowest point on the phase diagram. And so areas between 2.14 weight percent carbon and 6.7 weight percent carbon on that phase diagram happens to have a lower melting point than things that are less than 2.14 weight percent carbon. Okay, so it turns into completely liquid at lower temperatures than lower carbon alloys. And that's why it's called cast iron, because you can melt it and cast it. Casting is just taking a liquid, pouring it into a mold to form your solid. Okay, so cast iron is iron that's more easily cast because it has a lower melting temperature. And so cast iron, obviously, it has a different microstructure because it doesn't go through the pure austenite phase, right? When you're solidifying it, lowering the temperature, it goes into the austenite plus cementite phase before going into the ferrite plus cementite phase. So it's going to have a lot more cementite compared to your lower carbon steels. And so cast iron generally are very, very hard. They behave almost like a ceramic material, right? They're hard, they don't bend. It's very difficult to, essentially cast iron, they don't deform. They just break, they're brittle. They behave more like a ceramic material than a metal because of the high amount of cementite. And then we have a few other interesting alloys. We have copper alloys and brass plus zinc. If we have weight percent of zinc is less than 35 weight percent, we have something called alpha brass. And that's FCC. And then if you have higher weight percent, you have something that is alpha plus beta prime. And beta prime is BCC. Okay? So you have two different kinds of brass depending on how much zinc you have. At lower amounts of zinc, you get an alpha phase, which is a FCC, phase center cubic. At higher percent of zinc, you get a mixture of alpha plus beta prime. Alpha is still FCC, beta prime is BCC. Which phase, beta prime or alpha, would you expect to be more ductile, to be able to deform more easily? The only information I've given you is crystal structure, right? One is FCC, one is BCC. So the only way you could decide which one is more ductile is based on crystal structure. So why FCC is more ductile? Okay, why is that?
It has more slip systems.
Great. FCC has more slip systems. FCC is a more tightly packed crystal structure. It has more slip systems, more directions in where dislocation movement can happen. BCC is a less tightly packed crystal structure, so it has limited number of slip systems. So in general, BCC materials will be less ductile than FCC materials. Very good. So we have these two materials. So if you have higher amount of zinc, you're going to get a less ductile material because you get both a phase that is less ductile, plus also you have a mixture of phases, so you have probably more grain boundaries. Okay? So alpha brass is usually more ductile than the higher weight percent zinc brass. Then you have bronze. That's also a copper alloy, and that's copper plus tin plus some aluminum, silicon, and nickel. Bronze will be usually stronger and harder than brass because you have more alloys, more defects or impurities. And also, you have some material, it will be more corrosion resistant than brass because you have the aluminum tends to form just like stainless steel where the chromium forms an oxide layer and protects the rest of the steel. Aluminum tends to form an oxide to protect the rest of the bronze. Then you have aluminum, magnesium, and titanium alloys. Okay? And they have different kinds of properties. Those three are generally pretty light. Magnesium alloys are really light. Aluminum alloys are light as well, and so are titanium alloys. They're generally corrosion resistant. They usually form some sort of oxide layer that can protect the rest of the material. So the metal aluminum is extraordinarily corrosion resistant. And the reason is because it corrodes very easily. So it forms an oxide layer really fast. And that oxide layer is very, very compact. So it doesn't allow any oxygen to go through. So you take a piece of raw aluminum, it's going to form that oxide layer really fast over the surface, and no more oxygen then can penetrate through that layer, so the rest of the aluminum does not corrode. Okay, so it has a really high corrosion resistance because it forms that oxide layer so quickly. And same thing with magnesium and titanium. They're similar in that behavior. So I want to talk a little bit about how you're all working on material selection, right? The material selection project. I want to talk a little bit about how engineers have worked on material selection in the past. So does anyone know what this airplane is? No one knows this airplane? Some of you? No one's seen it before? So this is a real plane. It kind of looks a little bit like a Marvel movie kind of airplane, right? But it's an actual plane, and it's not brand new. It was actually built in the 1960s. So it's a very old plane. It's called the SR-71, or the Blackbird. Okay, so it was developed in the 1960s during the Cold War between US and Russia. And it was developed in an area in California called Palmdale under Lockheed, the company Lockheed Aerospace, and in their Skunk Works division. They had a division especially for developing innovative, state-of-the-art airplanes. They were calling it Skunk Works, and that particular division operated out of Palmdale, which is a desert area in California, about 2 hours north of Los Angeles. So during that time, in the 1960s, the US really wanted a plane. The SR stands for Strategic Reconnaissance. Reconnaissance just means to like spy, basically. So this is essentially a spy plane. Okay, it doesn't carry missiles, anything like that. The point is not to fight. It's just to spy. So it has very, at that time, very advanced camera equipment on the plane so that it could just fly over enemy territory and see what they're doing. Okay, so it's a spy plane. And in order to not get shot down when flying over places that it's not supposed to fly, and it has to fly very, very, very fast and very, very, very high. And this plane actually, even though it was made in 1960s and it was retired in 1998, so they no longer fly this plane, it still has a lot of the flying records. It's the highest flying aircraft, and it is the fastest flying aircraft still today, even though it was built in 1960s. They no longer use it because now they use satellite reconnaissance and drones. This is a human-piloted airplane. And so they no longer need to make airplanes like this. They use other things. So it can fly from New York to London in under 2 hours, so across the Atlantic in 2 hours. And it can fly sustained at 26,000 meters. So you could see it actually, from the airplane, you could see the curvature of the Earth. So it's almost like being in outer space. It's like just on the edge. That's how high it flies. And it flies very, very fast and very, very high, and that's how it evades both radar and surface and missiles. So it doesn't have to have a lot of like maneuverability to avoid getting shot down. This plane, even though it flew thousands of missions between 1960 and 1998, it has never ever been shot down because it basically just outflies the missiles. It flies faster than the missiles, so missiles can't catch up. So I'll show you a short video, and then we'll talk about the materials required to build this plane. Okay, so the SR-71 can fly at Mach 3.3 sustained. Right? This is not a top speed. It could just fly at 3.3 for up to 90 minutes. The reason why it's 90 minutes is because at that point it runs out of fuel, and then it has to refuel. And the way it refuels is in air. So it slows down, another airplane comes above it. It has a boom, a little stick, and the SR-71 has a little hole on top. It aims the boom into the hole, and then it can refuel in air. And that's how it can fly for 11 hours straight. It's by refueling multiple times in air. The biggest challenge with making the SR-71 is actually not the strength of the material. So it needs obviously a very strong material to fly an airplane that fast. It needs it to be fairly light so it doesn't take a lot of fuel to get it off the ground. But the biggest issue that the SR-71 had was the heat generated from flying so fast. So most materials would not be able to take the temperatures that the SR-71 flew at. So what they did was that they looked around, they said, okay, we need to have something that's light, that's strong. The strength to weight ratio that's required actually can be satisfied by steel or aluminum, but the heat resistance, only titanium alloys had the ability to do this. In the 1960s, they didn't have a lot of experience working with titanium alloys. And I'll talk a little bit more about that, but basically they had to come up with all new ways of working titanium. And so it was really quite remarkable that they were able to build the SR-71 from design to production in less than 4 years, the entire plane. In June 1962, the US Air Force reviewed a mock-up. So June 1962, the US Air Force reviews the draft of the plane. December 1962, Lockheed signs a contract to build the plane. The official first flight took place in December 1964. So a very, very shortened amount of time to build a plane that no one has built before, that can fly higher and faster than any other plane, and also using new materials that no one has used before. And in fact, this plane, when titanium heats up when it's in flight, it expands. Just like any other material, there's a thermal expansion, right? And it expands so much that it would buckle if they were to build a plane very, very, like where all the pieces fit. And they also couldn't find a coolant that can operate at the temperatures that the plane flew at. So they couldn't find a coolant that can stay liquid at those temperatures. So what they did was that they actually used the fuel as a coolant. The fuel can stay liquid until it's ignited, so they would flow the fuel all through the body of the plane and then feed it into the engines. Okay, so from where they store the fuel, they flow it through the body and then feed it into the engines. So the fuel was a coolant. But because they're flowing this through, the body needs to fit very tightly, but they can't make the body fit that tightly. So actually, whenever the SR-71 is on the ground, it just leaks fuel, because it needs to account for the expansion. So once it's in flight, it doesn't leak anymore because everything expands and fits together perfectly. But on the ground, it just leaks fuel. So they had to come up with a new material, and they chose titanium. So let's talk a little bit about titanium. So they picked the material. They said, okay, titanium alloys will work. It has a high enough strength to weight ratio, and it can be resistant at high temperatures. But how do they make this material? So the ore, so titanium comes out of the ground as TiO2, titanium dioxide. That's how it normally exists. Okay? So you get titanium from the ground, you're going to find it in the oxide form. It is very stable material. So it's thermally stable. You heat it up, it's not going to change. It's still going to stay titanium dioxide. It is very chemically stable as well, so it's very difficult to remove the oxygen from the titanium. So what they do is they take TiO2 plus chlorine gas plus carbons, a source of carbon, and this is not stoichiometrically balanced, but basically they form titanium chloride plus CO2. They take titanium oxide with chlorine gas and carbon, and they form titanium chloride plus carbon dioxide at high temperatures. And then they take the titanium chloride and they mix it with magnesium at around 1,000 degrees Celsius. It turns into titanium plus magnesium chloride. So those are the two reactions that they do to get titanium. Chlorine is a very toxic and corrosive gas, and so this process is very, very expensive and also very energy intensive. because everything has to be done in sealed containers, make sure nothing leaks out. And this is very reactive to oxygen. So if you let any amount of oxygen into these reactions, you're going to form titanium dioxide. And then you'll have to start over again. Okay? And so it has to be in a really tightly sealed container with maybe inert gases to fill in the rest of the space. And then once you get titanium in this way, you get titanium in a sponge-like format. So it's very porous. It's not a single sheet or a big chunk of titanium. You get titanium in a sponge-like material, so you need high temperatures to press it into a sheet. But at high temperatures, you usually need to have heat, flame of some sort, right? And usually with a flame, you need oxygen as a fuel, right? Heat usually requires oxygen to form. And so you cannot use any sort of regular form of heat because that requires oxygen. At high temperatures, oxygen will react with titanium. You get titanium dioxide. And so what they have to do is they use an electric arc that doesn't require oxygen. So they use an electric arc to heat up the titanium inside a container that does not contain oxygen. And then they press it into sheets or other forms that you can use. Okay? So all of this is very expensive, takes a lot of energy, and takes a lot of development. So these are the things that they didn't know before they decided to build an airplane out of titanium. And other things that they found out along the way is that titanium reacts with chlorine in water. So they were using water to cool down things that they were building, and they realized that you were getting titanium chloride, and it becomes brittle, and so they had to use distilled water in everything that they did. And then also that a lot of the tools, cadmium, in the tools that they were using to drill holes into titanium or to cut titanium or to bend titanium caused corrosion. So the cadmium reacted with the titanium metal and caused corrosion, so they had to actually go through and replace all of their tools, all of their cutting tools, all of their bolts, with materials that did not contain cadmium. So all trial and error as they were putting these things in. So when you're thinking about your material selection, I'm not going to ask you to think about all the potential problems because obviously those comes through trial and error, but just to be aware that whenever you're using a new material in an existing application, it's not just as simple as saying, okay, this material is cheaper, so I'm going to use this material, or this material is stronger, so I'm going to use this material. There are a lot of other considerations it needs to fulfill, right? It's not just the strength, it's not just the cost. It is how are you going to get this material? How will you process this material? And also, once the material is put in place, how does it react with everything else that happens around the material? And the manufacturing, also, because titanium is so strong, the strongest tool that they had to work on metals at the time could only provide up to 20% of the forces that were needed. So they had to build brand new machines that can press the titanium with higher force. So lots of things like that. They were finding that the drill bits, because titanium is so hard, the drill bits were becoming dull, and that they could only use them 17 times before they had to throw away each of the tool bit because it was dulling. Okay? And so things like that they had to really work on. And another thing is that because titanium happens to have very low thermal conductivity, so it doesn't transfer heat well. So when you drill a piece of steel, usually use water to cool the area, and the steel also radiates the heat out. The steel is a very good thermal conductor, right? And so the heat gets spread out, and you put water on it, the heat goes away. But titanium has very low thermal conductivity, so that means when you drill a hole, all the heat just stays around where you're drilling. It doesn't get shared. So it gets very, very, very hot. And that heat also dulls your drilling bit because the drilling bit becomes super hot at that area. So all of these things that they had to figure out when they were building the SR-71. So the titanium alloy that they use is alloyed with chromium and aluminum and vanadium. So it has 13% vanadium, 11% chromium, and 3% aluminum. Chromium and aluminum are there to form an oxide layer to prevent corrosion. And the vanadium stabilizes, so this is corrosion prevention or resistance. And the vanadium is to stabilize. The titanium they want to use is the beta phase, and if you add some vanadium, it stays in the beta phase more, easier to form. So this is a typical material selection diagram. The material scientist will consult. What's on the X and Y axis depends on what you want. So if you were looking at strength to weight ratio, you will use something like this, right? You have strength versus density. Obviously, the higher the density, the heavier the weight would be. So if you want high strength to weight ratio, you will want something that's high on the y-axis, but low on the x-axis. Okay. And you see that usually the lighter the material, the lower the density, the lower the weight. So in order to get really high strength to weight ratios, titanium alloys are here. Aluminum is here. Okay, so they're both very high strength to weight ratios compared to something like copper or tungsten or lead, zinc. Okay, so you would look at a diagram like this depending on what kind of material properties you want, and you could select your materials that you might want to try out. Another material or application is the James Webb telescope. Okay, so this launched recently, not too long ago, right? Any of you been following the James Webb telescope? So I want to show you a short video about that. So the first part is about the heat shield. So the James Webb telescope, the purpose is to collect as much light as possible from as far away as possible, right? So they're trying to look into the very, very distant past. And from very, very distant past, the photons that they could get are very, very few. So they needed a really large mirror that could collect the few photons that are available from such a distant past. So they need to collect a lot of light, so they have to have a really, really big mirror. And in fact, the mirror is about 5.5 times the size of the Hubble Space Telescope. So the previous telescope is the Hubble. The James Webb, the mirror size is 5.5 times the size of the Hubble, so much, much bigger. To send that much weight into space is very, very difficult. So they actually chose the Hubble uses glass, basically, as the mirror. And we'll talk a little bit later about the different material they chose for the James Webb, because it can't be 5.5 times the weight. It'll be too much. And so they actually chose a different material. So even though it's 5.5 times the size, it's only 38% of the weight compared to the Hubble Space Telescope. So they chose a different material for the mirror. And then it needs a really large heat shield so that while it's operating, the mirror doesn't get heated up by the sun. Okay, so it talks about what kind of material they chose for the heat shield and then what kind of materials they chose for the mirror. Heat shield first. So they chose beryllium because as the mirror, the backing of the mirror, not the reflective part, because it needs to go from launch temperatures, right, high temperatures, into space, which is very, very cold, without changing its shape much. So it can't expand and contract like titanium does, because then it will ruin the configuration of the mirror. So it needs to be able to hold its shape. It needs to be very light, and then it needs to be very, very stiff. And so beryllium fits all of those things. Beryllium is toxic to people. So beryllium, that made it very difficult to make something that big where all of it is toxic. And so the handling, obviously once it's in space, it doesn't matter, but the handling, the transport and the manufacture and sending into space, all of that, they had to consider the fact that beryllium is toxic. And it's also not reflective, so they had to coat it with gold. But because of the new, they actually hired 2 different companies to propose how to make the mirror for the James Webb. And one proposed glass that's similar to the Hubble Space Telescope. They talked about how to make it so that it could be very stiff, but also thin, so that it could be lightweight. But still, another company proposed beryllium, and NASA chose the beryllium to go forward. And so far, it's worked out really well. The James Webb Space Telescope has been sending back lots and lots of interesting images of faraway places and also things from a long time ago. So that's all I have for you today. And then next week, we'll talk about some of the other materials that we haven't touched on, so polymers and ceramics.